My name is Junshik. Everyone in this room talks about the very large-scale models. I'm gonna scale down. Actually, today my topic is about in-situ aircraft cloud measurement. And why do we need these blue waters, like a very big supercomputer for airborne observations? I will explain it through this presentation. Okay. First, the sun is our only energy source, and it interacts with clouds. And cloud shows lots of temporal and spatial variability. And to understand the climate system, we should know about this radiative property of a cloud. Cloud consists of these cloud particles. For example, low warm cloud has liquid particles. It has a spherical shape. And high thin ice crystals has these non-spherical ice crystals. In mixed phase cloud, these cloud particles coexist. And we using aircraft to observe these cloud particles. I'm going to start with size distribution. We call size distribution. It is number of particles in a sample volume and within a size range called bin. This particle size distribution is very fundamental input for numerical models and satellite retrieval algorithms. And typically, we observing this size distribution using cloud probes installed on aircrafts. About the particles larger than 50 micrometer, we use optical array probes to measure these particle sizes. For particles smaller than 50 micrometer, we use the forward scattering probe to measure particle size distribution. And today, I'm focused on these forward scattering probes. Okay, so forward scattering probe, how this forward scattering work is, when the particle pass through this sample volume, it shines laser beams, and there is a scattered light. We observe this scattered light in particular directions. And we assume that we know the shapes of this cloud particle and refractive index of these particles. For example, forward scattering probes was developed in 1970s. It measures particles size smaller than 50 micrometer. And there's a lots of different type of forward scattering probes, but all their working principle is the same. Different scattering probe has different measurement angles. For example, CDP is measured in forward direction, and CAS measure forward and backward direction. However, this forward scattering probes was originally developed to measure spherical particles, spherical liquid particles. So when we measure non-spherical ice crystal, there is unavoidable errors. Okay, let's see what's the problem. Okay, what really this forward scattering probe measure is a differential scattering cross section, and looks like this one. And then we can calculate this scattering cross section by integrating this P11, so-called P11 scattering phase function. And then we calculated this scattering phase function theoretically. And this figure shows that scattering phase function of spherical particles, and blue is the liquid spherical particles using meat theory, and red is we assuming ice particles using meat theory. So both are spherical shapes. And left one is the size of particle size of 2 micrometer, and right one is size of 10 micrometer. And for example, one of the type of forward scattering probe CAS measure forward scattering direction between 4 and 12 degree, and backward direction 168 degree and 176 degree. And this gray shaded area is forward and backward directions. We integrating this scattering phase function within these angles, and then calculate this scattering cross section. So this is the working principle of a forward scattering probes. What we forward scattering measure is scattering cross-section, and then we converting it using this conversion table, and then get that particle sizes, and then finally we get the particle size distribution. But to generate this conversion table, we using mean theory and assume spherical shape and refractive index, unknown refractive index. Okay, and then this is the conversion table, a current conversion table of a forward scattering probe. So red one is the ice and blue is liquid, and it has different refractive index, and both has a spherical shape. And left one is the forward scattering direction, and right one is backward scattering directions. And then what is problem? Let's see. So when we have one single measurement here, and then there is multiple solutions are possible here. So we can get the multiple selection of sizes of these particles, and this is a big problem. And right now what we are doing is using this simple linear fitting curve to find the one single solution, or we averaging over these multiple solutions. And then estimate error is about near 20%, but this one is using a best fitting curve. This is the known errors. We already know this. This one is the errors due to misscattering for spherical particles. And then next question is, what about non-spherical ice crystals? Let's see. So this is key challenges. Now, ice crystal can be a spherical shape in very, very rare case, but most cases is non-spherical shapes. For example, hexagonal shapes are very fundamental shape. That is due to the hexagonal lattice structure of molecules in ice crystals. And in cloud chamber experiment, 6% of ice crystals had hexagonal shapes in growth rhythm. And in very few studies, as far as I know, there is only two. Two studies have tested the uncertainty in forward scattering due to the non-spherical shapes of ice crystal. And this study shows that errors is less than 20%. But these studies are based on the T-matrix calculation, assuming ice crystals are cylinder or spheroid. But look at this real ice crystals. They are not cylinder or spheroid. This is due to when we try to find the exact solution of this Maxwell equation of for non-spherical particles, it requires lots of computing resources. For less expensive T-matrix method is limited only to these axially symmetric particles only. But this hexagonal shapes has a 6-fold symmetry, so T-matrix cannot calculate scattering properties of these hexagonal ice crystals. In alternative solution, we have called discrete dipole approximation. It's called DDA. It can calculate the exact solution of any shape of particles. However, as computing time and required memory increase dramatically with particle size, so we need large computing resources like blue earth. Hexagonal ice crystals is defined by length and width and its ratio called aspect ratio. In this study, we consider these 6 different aspect ratios, so from thin plate, long columns. Then we use the Amsterdam discrete dipole approximation ADDA, and then we calculate the scattering phase function and forward and backward direction scattering cross-section, so CAS. Then this is the hexagonal ice crystals consist of dipoles, and blue box is magnitude images. So we assigned each or groups of these dipoles to course of blue waters and then calculate the scattering properties. Then I'm going to show that what we done using blue waters. Okay. This is new conversion table, and left one is forward scattering direction and right one is backward scattering direction. And blue and green is the current one. So blue, red and green is the current conversion table. Red is the me using me theory, and we assume the spherical liquid shape, and the green is the spherical ice crystals using me theory, and blue is the new one, is the hexagonal columns using ADDA. And each panel represents different aspect ratios. So errors increase with this non-sphericity. I mean, the either oblate or plate shape shows a much larger errors compared with this compact shape of aspect ratio of 1. Next figure shows the same figure, but it shows the difference in diameters, so errors in percentage. So blue dot is average error, and red one is maximum and minimum errors when there are multiple solutions are possible. So which shows that average errors is up to 41% in forward scattering direction and 63% in backward direction. And these errors are large enough, and we should consider these errors in forward scattering observations. Okay, and this is my summary. Calculate the error due to non-spherical shapes in forward scattering probe observation is larger than what due to the mis-scattering. And then we show that up to 41% in forward scattering directions. And right now I'm building new conversion table. And in this conversion table, I also consider particle orientation and polarization information to distinguish particle size and thermodynamic phase. For example, this bottom figure shows the left one is a hexagonal column and right one is ellipsoid. And this figure shows the linear depolarization ratio. So this one is polarization information. And they are exact same size, but they show the very, very different this polarization information as a function of particle orientations. Okay, yeah, that's all. I'm gonna stop here.